Hey folks, I'm going to help you out with talking through section 4.4, number 75. It's ebb and flow problem. It's a great problem, just a lot of information. Let me just read the problem to start with. It says, on a particular Labor Day, the high tide in Southern California occurs at 7:12 a.m. At that time, you measure the water at the end of the Santa Monica Pier to be 11 feet deep. At 1:24 p.m., it is low tide, and you measure the water to be only 7 feet deep. Assume the depth of the water is a sinusoidal function of time with a period of a half a lunar day. Now, we always think of 24 hours as a day, but a half a lunar day is going to be about 12 hours, 24 minutes. So a little bit more than half of a typical day, 24-hour day. So then it's asking us all sorts of questions like, at what time at Labor Day does the first low tide occur? And when we talk about that, we're talking about the first time after midnight. And then when was the approximate depth of the water at 4 a.m. and so on and so forth. So let's first just get our information started on Notability, or at least that's what I'm going to do. And I have some information already written just to save a little bit of time. So again, this is section 404, number 75. We're talking about time in hours and height in feet. We know the period is a half a lunar day, which is 12 hours, 24 minutes. I'm going to convert that over to just purely hours. You can also convert it over to minutes if you want, but I'm going to use hours. And once I have my period, and again, if you don't, 12.4, you just take that 24 divided by 60. So 24 minutes over 60 minutes gives you the part of the hour, which is 0.4. Just kind of making sure you don't think we're base 10. We're definitely base 60 on the time spectrum. Anyway, so the period is 12.4 hours. That means that the frequency, and this is where I'm going to start here, and remember, if you like to just tend to not to try to remember too many things. The period is equal to 2 pi divided by the frequency. Since I know what the period is, I'm going to erase that and replace it with that 12.4 and solve for b. So the frequency will be pi, well, first of all, it's going to be 2 pi over 12.4, but you can simplify that down to pi over 6.2. So that is our frequency, which is not pretty, I understand. So here's what we're going to do. We're going to now kind of take a step back here and kind of draw out what we have for the information we know. Like for instance, we know that at 7:12 a.m. we have a high tide. And I'm going to switch that over to hours just to make it again a little bit easier for me. So 12 divided by 60, we're going to talk about 7.2 hours after midnight. So I'm going to plot that. So 1, 2, 3, 4, 5, 6, 7.2 hours. We're at our maximum, and our maximum we know is 11 feet. So I'm going to actually even do one better, just like I've been always doing, getting that max line there. And we have a point right there. That's our max. We also know that the min was, oh, I already forgot, 7 feet. So I'm going to put that right here. And my daughter just walked in and she's wondering who I'm talking to. Is 7 feet, and then the midline is halfway between the two. So there's my midline. And so halfway between the two, and keep in mind that this is where your amplitude's coming from is going to be 2. So that's 9 right here. So what's nice now is we do know our B value or our frequency. We know our amplitude. Just doing a little bit of picture work kind of helps. And again, the amplitude is 2 feet. So it's fluctuating either going up from 9 or down 9 by 2 feet. What else do we know? Oh, we do know our vertical shift, which is 9. So really, it kind of goes back to that where exactly or how do we shift it back so that we can actually see what we need to see. And you can do this a couple different ways. And actually, before I do that, we can answer the first question, which is at what time on Labor Day does the first low tide occur? Well, if you know this is your maximum right here, you can work backwards and notice that, where are we at? This is 7.2 up, right? Or over, 7.2 hours. If I take half, because we know if that's the max, the min's going to happen in half of a period. And again, 12 hours is a full period, so half of that is 6 hours, or excuse me, we can just say 6.2 hours. So go back 6.2 hours, and that's going to take us at 1 a.m. And you know, I'm doing a little bit of like mental math there, but really, if you just kind of think backwards, like if your max is um, at 7 a.m. or a little after 7 a.m. and work backwards from there, you can find your min pretty easy. So let's kind of draw that graph. So again, we know at 1 a.m. we're at our minimum. Ooh, I just erased that. That's what I do not want to do. Let me switch back over. So at 1 a.m. or 1 hour after midnight, I'm at my minimum. So this is 1 hour after midnight. And then again, I'm going to draw a nice little curve here. It's not going to be the most beautiful thing ever, but it'll get my point across, I think. And then it's going to keep on going, obviously. Oops. Yeah. I am not that good at drawing on this thing. Okay, so again, we know that from, in case you missed what I had said there about how I got to 1 a.m., is that the length from the minimum to the maximum is going to be 1/2 of that period. Because of course a period is from like this minimum back to the minimum. So I'm going halfway through. And half of my period is going to be 6.2 hours. Using this right here, that 12.4, splitting it in half. And so if I take this right here, which is 7.2 hours, and subtract 6.2 hours, it gives me 1 hour after midnight. So again, this is like at 0 time or midnight. Okay, so that's where I get that, and we're kind of in the money now. Okay, so let me just kind of, so letter A in the problem would be 1 a.m. because of everything I just said. Letter B, it says what was the approximate depth of the water at 4 a.m. and at 9 p.m. This is where you're going to have to use, kind of like I demoed the other one, Desmos or your graphing calculator, and find the intersection between the function and those times. So let's create the function so you have that. So we have y equals, again, our amplitude is 2 cosine. We know that our period, or excuse me, our frequency is right here. So that's going to be pi over 6.2, and then that's time. I have to shift this. This is the thing though, you guys. I have to shift this so that I have some sort of reference point. I'm going to shift this, where am I at? I know that this maximum point right here, this is the $1 million point. That's the big piece of information. I know that's at 7.2 hours. I'm going to shift it back this way so that that is right here at that max point for the cosine. So I'm going to go plus 7.2 hours. And then, of course, we know our vertical shift is 9. So if you were to graph this in your y sub 1 and then in your y sub 2, actually, never mind, what am I saying? You just need to, at this point, for this problem anyway, for letter B, put in the times now that you are interested in. So 4 a.m., so that's where you'd say the time is 4 hours after midnight, or 4 a.m. And then the next one, the second part, you would substitute the time of, well, 9 p.m. So where is that? That's how many hours after midnight? So that's where you have to be careful, right? So let me just actually put in this 4 in for 4 a.m. and that's going to give you 8.9 feet, and I'd expect to see you throwing that in there. And you could, again, still use Desmos and so on. That's always really good. But again, 9 p.m., so starting from midnight to midday, you're talking about 12 hours plus another 9 hours to get into the evening. So just to kind of make sure you understand what I'm talking about. So 9 p.m. is really talking about 12 hours plus the 9 hours. So this is in the morning, this is in the evening. So you're going to actually put in 21 hours after midnight into this function right here for t. Now the last one, letter C, that's definitely where you have to use your Desmos or your, I'm sorry, I keep saying that, graphing calculator. What is the first time on Labor Day that the water's at 9 feet tall? So this is where you're wanting to know when it's 9 feet deep. So this is where you would use your graphing calculator and actually put it in and find the intersection between the function right here and this right here. So that this would be y1, this would be y2, and you'd find your intersection, and you'd find, actually, now that I think about it, I don't really have, I have to do the calculation really quick. You'd end up with an intersection of 4.1, and you'd have to convert that over to a time, which is 4.06 a.m. Okay, so this I would expect you to be able to do at this level. So again, the big thing here is take the information given, graph what you know, figure out, in this case, your frequency, your amplitude, your vertical shift. Once you graph it, then you can figure out your phase shift by getting it that maximum point, this one right here, back to where you need it. And then from there, once you have a function, then you could plug and chug anything you want in it or use your graphing calculator to find solutions as well. So hopefully that helped with that problem, at least for the setup. Any questions, you know where to find me. Take care.